Yeah, Ozzy, good boy. Yeah, don't let him have it. Ozzy, leave it. That's rude.
These taste like sugar and disappointment. The national taste of Valentine's Day.
Go ahead.
It's that chocolate. Yeah. Chocolate filled with
I actually got the chocolate
They got skinny something that the others do.
Yeah, he knows it. Ozzy, enough with the Jedi mind control. No, come on. Hey, leave it. You're being super rude. Leave it. Yeah, he's a brat. It's his problem. Why did it not go? Told it to go. Winnie, what? Oh, physical science is fun. You'll enjoy it. All right, are y'all good to go? About ready here? I hate that this thing's always in the way. I want to make this small. Get that away. Woo.
I was gonna say dog food.
Can't make this. All right, so if you're done with your timeline, you can put it up on the counter and put that back in your binder. And we got to start in just a minute. What's that wrong with the internet? Oh, Alex, dude, that's so like first grade. Don't do that, man. That doesn't do you any good. For real. Oh, it's gonna be nice and let me in. It's just very slow. Why it's being like this? For real, right? Oh, man.
But not me.
It's not old.
Hey, between me being the killer in the horror movie and me just running straight the killer and stabbing the killer. No, you're the killer. I either be the killer or I just say screw it and stab the killer to death with their own weapon. Yeah.
So this is the guy I've been letting dry. Still pretty hot. But I'll leave it up here on the counter. So this, y'all back there. So that's should be a shoulder blade. Would be like there on a deer, right? And so anyway, this one's interesting. If you get a good look at it, stay, I'm gonna let it cool down a little bit. Then I'll probably warm it up one more time and try and dry it again a little later. But if you look around the edges, there are all these little like little parallel gouges where something chewed on it. Some small animal with little teeth nibbled all around the edges here to pull off whatever flesh was left. Wow, yeah, right. But this is the big prize this year. So it's a pelvic girdle, the whole pelvic girdle. See, and then the spine. And one of the cool things about this is one of the things that hung on and didn't deteriorate is this intervertebral disc. Yep. When it's wet, it looks like packing material. You can see all of the collagen fibers like They go this way and then they go this way, kind of like like I have a cable over there for my phone that stretches and bends easily, but it's really tough. It's like that kind of idea. Yeah, it's like a weave. This bone now that I've heated it, this femur bone has got a crack that it didn't have earlier, so I probably should have drilled a tiny hole in it somewhere. But that crack was not there before. But this is how the femur bone articulates. It would be right here. So I put a screw in it. There's a tiny piece of cartilage left that didn't detach. Oh man, it cracked bad. The pelvic girdle didn't crack, however, because I had multiple holes in it. Here where I articulated this bone. And then through here. And this is actually this aluminum gauge wire is flexible. I don't want to bend it now because it's kind of hot and a little brittle, but you can actually see how the vertebra move one to the other. And this is where the vertebrae attach inside the pelvic girdle. So I went ahead and screwed that in so it's permanent. And I ran the other wire from here down to there. So this would be where the tail would start. If you have like an animal with a long tail, deer have that little tiny tail, but still, it's kind of cool. I think it's pretty cool. And you can definitely see there's a space here based on how it articulates at the top. There's a space here where the disc would be, right? Because this one's still here, and this is where they fuse. So that's kind of cool. But it would be roughly like this, because you know the deer's back leg goes this way, and then its front part of the leg bends a little. So it would probably be around this position resting, which is kind of cool. I like it. So anyway, I'll put it up here and you're welcome to look at it. Just be real gentle with it. I'm gonna have to make a little hole in that femur before I dry it anymore because it's obviously not sticking well to that. It cracked. It was perfect. So I thought about it first. And I thought, no, just drill it because what if it comes out perfectly and you don't have to drill it? But no, should have done it. All right, so let's let Sky in. If she will. All right, and I have to put your hand back. Let me see. Parker. I'm not sure what that was. You tell me what that is, I'll do whatever you want me to do with it, but I didn't know what it was. It had your name on it. Is it extra credit? Okay, so you need to write down that page number, so the questions, so I know what to do with that. And Milo, where'd Milo go? Oh. This is you right here. Okay. All right. Did this ever do its thing? Of course it didn't. It hates me. I don't know why. All right. Probably because it's like 15 years old.
There's always like 1%.
Yeah, it happens. No big deal. So we're going to talk about Precambrian Earth. And these next couple geologic time lessons, they're kind of fun. Because, you can have a little dinosaur feet. And that's interesting. I don't know about y'all, but I'm tired. I think I might have me a pizza for dinner. Pizza sounds great for dinner tonight.
I've had pizza 2 out of the last 4 days, and I'm still hungry. Pizza's so great.
What kind of pizza do you like?
I forgot.
Oh, there are some people paying attention. We'll see. You have no idea what just happened. Something you should be doing every week that you may not be doing.
I like barbecue.
You like barbecue chicken? Where from?
Pizza and wine.
Ah, okay. I don't know. I like veggie pizza. All right, so let's see. Put it on. So first, we're going to start with the big picture, all right? Because we're going to be breaking down geologic time into smaller chunks. We're talking about this whole formation of the planet to how we got to today. So we're going to take like a big step back and look at it from far away for a minute to kind of get ourselves in the realm of what we're doing. And this little chart that keeps falling off that came with all those fossils there, it's a reminder of kind of how things break down, at least as far as fossils are concerned. All right, so how did planet Earth form? Make sure I got volume right. I'm not sure yet. Oh, hey, Dad.
Millions of pieces of the inner planet blast outward into space.
I don't think that was the beginning.
Trapped in the Earth's
Nope, it
gravity.
was not. Hold on. Stamp it. There you go. Move this out of your way because you can't see through that. All right.
4.6 billion years ago, an enormous cloud of gas and dust called a solar nebula swirls in the Milky Way galaxy. A new solar system is born, our solar system.
Yeah.
Right?
In a process known as the conservation of angular momentum, gravity collapses the cloud, turning it into a flattened, spinning disk. The powerful gravity pulls most of the gas into the center of the disk, and this gas gradually condenses, coalesces, and ultimately forms our sun. Leftover gas and dust swirls around and slowly begins clumping together. Now the strong solar winds blast outward from the sun, blowing lighter materials like hydrogen and helium far out. Heavier material like dust and rocks resist the solar wind and remain close to the center. And it's this heavy material that begins clumping together, eventually forming the prototypes of the inner rocky planets, including planet Earth. It's the Earth's dense, rocky core that forms first. Heavy materials like iron and nickel gravitate to the center, whereas lighter materials drift to the outside, eventually forming the Earth's crust. Over millions of years, the new Earth begins trapping stray gas in its powerful gravity, and this gas eventually becomes our sacred, life-saving atmosphere. But suddenly, around 1 billion years after the Earth is formed, Theia, a large Mars-sized body, floating freely in the new solar system, crashes into Earth, causing near catastrophic damage. Millions of pieces of the infant planet blast outward into space.
Back on, Tia.
Some pieces become trapped in the Earth's gravity, ultimately becoming our moon.
America.
Today, comets are rare in the inner solar system, only appearing a few times every several decades. But during the early primordial times, comets were very abundant throughout the entire solar system. It's believed these icy comets colliding with the young Earth were the initial cause of water on our planet's surface. Of course, since then, Earth has become the pleasant, life-bearing planet we know as home. We enjoy an abundance of vegetation, water, tools, and technologies. We live a safe and protected life under our atmosphere. That is, until the sun turns into a red giant, incinerates the entire planet, and wipes out all evidence that Earth ever existed. But not to worry, we've got 5 billion years to figure that out, and we can discuss it in another episode. It takes weeks to make videos like this for you to enjoy. Do us a favor, comment, share, and subscribe.
So one day the sun will destroy everything.
So what I'm hearing is they throw rockets on Earth and push it away.
Right. So if we suspect that Earth is about 4.5 billion years old, and we suspect that the sun's going to do what the sun's going to do in about 5 billion years, then we can say we are about middle-aged. Right? Which question? Saturn will become Earth? I mean, I think the whole solar system will kind of go kapoof. Yeah, I don't think much in the solar system is going to survive. Yep. All begun. Yeah. So let's talk a little bit about early Earth. All right. So how do we know how old Earth is? All right. So Earth, the Precambrian era, sorry, I can't speak this morning. Precambrian covers almost 90% of Earth's history. So when you look at it, like sometimes there's like this right here is a great example. It's putting in Precambrian, and it's tiny, but it's 90% of the Earth's entire history. If you look, these little red marks, it says millions of years ago. So this is 4.6 billion to 544 million. And then everything else has happened since 544 million. And remember last week we talked about, how big is a million? How big is a billion? So really, this part of Earth's history is pretty much all of it. And if you look here, there's a little, it says if you go like from your shoulder to your middle finger, like right here is where you start bringing in other time periods. This whole length of your arm would be a one way to measure it. So how do we know? How do we know how old Earth is? So we have some crustal evidence in a particular mineral. What's our oldest mineral, Yusuf?
Zircon.
It is zircon. So zircon is the oldest mineral on Earth. It's stable, commonly occurs in granite, and it's used for dating the oldest rocks. It survives erosion and metamorphism, and it can date Earth's rocks as far back as 4.4. What's BYA? Yeah, billion years ago. Were you gonna say something, Alex?
That's Australia.
Yes, that's Australia. Okay, so we find a lot of zircon right there. That's where a lot of it is located. Now, zircon, you can find it other places, but this place, what's it called, Jack Hills in Australia, this particular area is just very, very rich with it. So here it is, Jack Hills zircon, and they're showing where it is and where it roughly within this timeline here. And this is all what time is this whole thing is what?
Earth.
Yeah, but where do we fit? Hadean, Archean, Proterozoic, and Phanerozoic.
Tail end of Phanerozoic.
Well, here's Phanerozoic right here.
Maybe to the 0.5.
So this is all Precambrian is what we're getting at. So all of this time period here, these are all chunks of that. So you've got your Hadean, Archean, Proterozoic, Phanerozoic, and these are all these little things. I mean, Phanerozoic comes later. They're
But yeah, this is
how do I
all
say it? Their chunk is not. It's right here is where they're bringing it in. But all this stuff here at the beginning here, this is the Precambrian, this side. So Precambrian over here, new time over here. Now I'm being clear. Clearly humans and things like that are not part of it. So over in here is where we're talking about. Here's moon formation, crash. Do we remember what the planet was that we think smashed us? Yeah, Thea. So we can find the oldest minerals on Earth right here, and it's in Jack Hills, and that happens to be in Australia.
But
Yes.
have you heard of Pluto World?
Eh?
No.
Is this a cartoon?
Oh, that's
Oh, that's going to be your project? Okay. All right. Pluto World, I'm excited
We
to.
are totally legitimate businessmen in case.
I am really excited to hear about it.
Kind of spaceship bus.
So what's some evidence in our solar system? Okay, so what is this metallic or silica-rich objects that orbit between the sun? That orbit the sun between Mars and Jupiter. What are these, Bailey? Between Mars and Jupiter, and they orbit. No, you had it. What? There you go, asteroids. Yeah, you had it. I know it was in your head, and then you're like, now I have an answer, and I can't remember it. So asteroids. All right. So these guys. All right. So when we see the diagrams of the solar system, you usually see, your couple planets. So what order do they go in? Mercury, Venus, Earth, Mars, then what? Asteroids, Jupiter, Saturn, Uranus, and then Neptune, and then poor Pluto is no longer a planet, and then it is, and then it's not.
But with our it's gonna be
Dwarf planet. Yes, we just, we'll take it out, and people were so sad.
With the rest of the universe.
There are t-shirts that say Pluto, never forget, and things. I love it. So anyway, all right. So what's some evidence? So let's think. Some evidence of within our solar system that tells us how old our planet is. So objects in space that range in size from dust grains to small asteroids. We can think of these as space rocks. Milo. Meteorites, meteors, asteroids. Yep.
Same thing as Mars.
Meteorites.
Ice?
Parker? Okay. That's pretty much that. Yeah. Meteors. All right. We got it. There we go. So meteors. All right. So these are these big old rocks. They can be big, huge. They can be teeny tiny. So once they've entered our atmosphere, however, and now they're flying through our atmosphere, or not just ours, could be another planet, happens to Mars too. And that friction from the air causes them to start burning up. They're fireballs or shooting stars, Bailey. Yeah, she's working to redeem. Anybody else? Yep.
Maybe meteoroids. I can't.
Wait a minute. What'd you say, Milo? Oh, yes. Comets. Hmm. Meteoroids or something. Okay. So
Rocks.
these are meteoroids. Okay. So this is where it gets weird. When they're floating around in space, they're meteors. When they're flying through the atmosphere and you can see them moving, it's not the meteor that is the meteoroid. It's the phenomenon of the meteor moving and making the fire. So it's a meteor still, but we call it a meteoroid because now it's producing a phenomenon. It's, burning through the air. Anybody ever seen one? I've been to they call it a meteor shower for a reason because they are meteors, right? You've seen them? Sometimes you can go when it's when they are frequent, like they'll tell you there's going to be a good meteor shower on this night, and if it's clear, you can get up at 2 a.m. or whatever and watch them. And sometimes you get up in the cold and go somewhere where there's no city lights, like the mountains, and you wait and you never see anything and you freeze and fall asleep in the back of your car. Ask how I know. So yeah, but sometimes you just look up and then suddenly there one is, and it's not predicted. You don't expect it. Oh, you went there. What were you gonna say? You said meteorites. Okay, so everybody's going for meteorites. All right, so if it survived the trip through the atmosphere, it actually makes it. It survives. It doesn't burn up entirely. It smacks into Earth. Yep. Okay. So these are meteorites. Do y'all remember a couple years ago, the one in Russia?
Yep.
I'm going to have to find video of that for you. I don't think I put it in slideshow. There was one that ripped through Siberia, I think, a couple years back, and it was astounding. I mean, it terrified everybody because it came in the middle of the day. It was loud. It was a big one. And it was like people thought they were being bombed. Eventually, I think, but not where all the people were that were screaming and filming it.
I don't think anyone's stupid enough to bomb Russia.
You never know, though. I mean,
You are putting a lot of faith in humanity.
It's true, and a lot of faith in Germany who have enjoyed that activity in the past. I was going to bring that up. Yep. What do you see there? Yep. If you want to see one that has not only survived its trip through Earth, but visited someone's house without knocking, there is one at Tellus. Tellus is up 75 towards Cartersville. It's a nice science museum. And they have one there. And I think don't they have the piece of the wall, or do they just have a picture of the wall? It came through. Like they were just chilling in their house and like, wham. Yeah, can you imagine? Like,
house guests for the rest.
For real, clearly. Yeah, that's what it is. It's the roof. Yeah. So if they survive the trip, they fall into Earth, and we can date them to 4.5 to 4.7 billion years old. So if we find one on Earth and it's that old, we know that at least what it formed from is that old. And plus, if we find them here on Earth, we know they've been hitting Earth for at least the length of Earth's existence. So some contain the first solid material to form in our solar system and have remained essentially unchanged since they were formed. And the Apollo rocks are 4.5 billion years old. What are the Apollo rocks? You know?
The moon.
Yeah, the Apollo was what mission? The moon missions. The moon missions were the Apollo missions. And so they got moon rocks, right? Everybody was like super excited, moon rocks. And some of those were meteorites that had hit the moon. Yeah. And those are 4.5 billion. Well, if these guys can be 4.5 to 4.7, but the Apollo rocks are 4.5, we know that the moon, or we believe, we've hypothesized and theorized, and it looks pretty good, that the moon was part of Earth, right? And it broke off in a collision, boom, and we have a moon. So if you're getting meteorites smacking into your planet that are between 4.5 and 4.7 billion years old, and the ones on the moon are 4.5 billion years old, well, the moon, I mean, obviously the Earth is going to be, this gives you an idea of where you are in the timeline, right? Okay, so why do scientists consider the age of meteorites when they try to estimate the age of Earth? Somebody give me James.
So the Earth, I think, formed at the same time as the meteorite. All the gas that I was talking about before.
Yeah.
From the same material at the same time.
There you go. That's perfect. That's a great answer. So, yep, most astronomers agree that the solar system, including Earth, formed all at once, and therefore Earth and meteorites should be about the same age. That's a perfect answer. All right, so dating rocks. Not taking them out for fun, but finding out how old they are.
The Earth is 4.565 billion years old, give or take a couple million years or so. How do scientists know that? There's no established in fact stuck on a cliff somewhere. No, geologists got there thanks to a handful of radioactive elements. With radiometric dating, scientists can put an age on dinosaurs and yes, even good old Mother Earth. So how do you date rock? Well, it's going to take some good chemistry. Lots of people have tried to date the Earth. Archbishop James Ussher famously used the Bible and a host of other historical documents to settle on the evening of October 22nd, 4004 BC.
Very
He was off by just a little bit. Things
highly
started to get
specific.
more
Yeah.
scientific during the Industrial Revolution. Geologists looking at layered rocks realized they were formed from gradual deposition of sand, silt, and other sediment, and that must have taken a long, long time. Once scientists came around to the idea, they tried some new approaches to deciding its age. Lord Kelvin had an idea to date the Earth by figuring out how much it had pulled down since it was formed. He settled on somewhere between 24 and 40 million years old. Better than Ussher, but Kelvin still didn't come close. One reason why is he didn't know that there was something inside the Earth that was actually keeping it warm: radioactive rocks and minerals. The discovery of radioactivity in 1896 paved the way for radiometric dating, which let scientists put an accurate age on just about anything, even a planet. To understand how, let's take a closer look at what happens to radioactive elements as they decay. We start with an atom of a radioactive element. Scientists call that the parent atom. When it breaks down, it releases, well, radiation. That transforms it into a whole different element, which scientists call the daughter atom. When you have a whole bunch of radioactive atoms together, the overall rate of decay from parent to daughter is constant. When half of the parents have become daughters, that's called the half-life of that element. That half-life is the key to radioactive dating. By counting the number of parent atoms of the
No, shut.
and the number of daughter atoms around it, scientists can figure out how long those atoms have been there. There could be a dinosaur bone, a big trilobite, or some other rocky, really old thing. No, not him. That's right. To get an accurate age for something that's old,
No, do not apologize.
geochemists have to be a little picky about which elements they go out looking for. The parent and the daughter element have to be stable enough that they'll both still be around after billions of years.
Don't be a jerk.
Otherwise, there'd be nothing to compare. Uranium is a popular choice for dating rocks. It's a radioactive element that's sometimes incorporated in crystals of zircon, a mineral formed as magma cools. Cubic zirconia also provides cheapos with a cloud engagement ring option.
There you go.
Uranium decays through a series of radioactive elements into a daughter atom, lead. Zircon doesn't incorporate lead while it's forming. That's important because it helps geochemists know that the lead they find in zircon comes from decaying uranium. So when they collect a rock in the field, bring it back to the lab and count the atoms in the zircon crystals, the ratio of lead atoms to uranium atoms in any zircon crystal tells geochemists when that crystal formed. But here's the thing. Geologists have never found pieces of Earth that have been around since the planet was born. Our world is an active place. Rocks are constantly being smashed and melted and reformed, so it's no wonder very little has lasted all that time. The oldest zircon we found is pretty close, somewhere around 4.4 billion years. So why do geochemists say the Earth is even older? Well, scientists arrived at the 4.565 billion years by expanding their dating pool. They use the same radiometric techniques to date meteorites. These space travelers are practically unchanged since the very beginning of our solar system, when they, the Earth, and the other planets formed. Since they don't have to deal with magma and weather and other geology business, the rocks on meteorites are a snapshot of the solar system's early days. Geologists love dating meteorites. We might even call them rock stars. They're like tiny crystals that crash into the Earth. The minerals in them can be radiometrically dated just like any others. And that, my friends, is how you date a rock. In less than 100 years, scientists went from numbering the Earth's age of thousands of years to billions, all thanks to a handful of elements and the scientists who revealed their secrets. Not that they're satisfied, of course. Geochemists are still fine-tuning their estimates of the age of the Earth and looking for more evidence to support or diminish their theories. But really, the only rock I have my eyes on right now is Dwayne "The Rock" Johnson. That guy's dream. Wait, one other thing. Happy National Chemistry Week.
That's not this week. That was another week. Okay. So Earth's estimated age is. Wait. And Jack.
4.5.
4.5. You want to get any more specific or you want to go right to that decimal?
I mean,
Got you.
I hate my answer off Alex.
No, Drew, go ahead. Your hand was up. 4.6. Yusuf? 4.565. So we're close. There we go. 4.54 plus or minus 0.05 billion years. Yep, right around there. 4.565. That video said. The textbook says something a little different because we're not sure. Once we get past this 0.5, we round up and we're not sure. So what are we basing the age on? Evidence from what? What? Okay, Liam? Zircon's a good one. Got meteorites. Piper? Yep. Base rocks, meteorites. Yep. Moon rocks. Yep. Moon rocks too. Okay, so there you go. So our radiometric dating is based on evidence from radiometric age dating of meteorite material and is consistent with the ages of the oldest known terrestrial and lunar samples. And then, of course, we had our zircon that we discussed too. All right, so Earth's early heat sources. Why was it hot? Okay, it's hot. Why was it hot? So let's see. So we have something called gravitational contraction. If I had my spinny office chair down here, I would show you, but I don't unless Cole wants to go grab the spinny office chair and bring it down here for me. Do you want to do that? Yeah, you do. You really do.
Yes.
Yeah, I forgot to bring it down.
If I drop that, you kill me.
He won't kill you. I'll tell him I killed you.
No, nothing to do.
Okay, well, okay, let's pretend. Anybody ever sat in a spinny chair and then tucked in?
Yes.
What happens when you do that? You go faster and faster, right? Okay, so that's a physics thing. That'll be something that comes up next year when we do physical science. So as that happens, as you start this whole rotating thing, you get this whole centripetal force that pulls it in. So as particles combine, the increased size, now there's more particles coming. So increased size is going to mean what? Who knows? You got two blanks here. Milo? Increased heat and pressure.
More friction.
Increased friction. Okay. Anybody else want to throw a guess? Parker? Huh? Milo's right. Okay. Yeah. So gravity and pressure. You're almost there. So why is there increased gravity? Because there's more what? Matter, which means there's more mass. Right. You got more mass. You got more mass. You got more matter. So now you've got more effective gravity because it's all coming in together. And you got pressure. And then you get increased, Milo. You said it. Heat. Okay. That's what happens when you squash stuff together. Okay. Now here's an interesting thing. Have you ever driven past one of these places that sell mulch for the yard and seen the piles smoking? Yeah. They've straight up caught fire. There's one over off, what is that, Shiloh Road or whatever, Majors, Shiloh down that way. And it's one of these big gardening centers. And they get these massive piles of mulch and they pile it up, pile it up, pile it up. And those things will start to smoke and they will catch fire because the mulch at the bottom, it's obviously flammable, it's wood. And it's under such pressure because the gravity's pulling it down that those pieces at the bottom start to get hot and they start to smoke and smolder. And then suddenly you drive by and this thing is like smoking. One day, one of them, because the boys went to preschool that way. And one day all the fire trucks showed up because one of them was legit on fire. Like a whole massive pile of mulch is just aflame now because they made it too high. So if you stack it too high, that's what's going to happen. Now, if it's nice and wet and it's been raining, it's going to smoke and smoke and smoke. But yeah, that'd be a thing. Oh, you got piles of mulch in your yard with your mother's gardening? You want to like,
you know where to get mulch.
you know where to get mulch. You have to make it really high, like 20, 30 feet, big, tall. All right. So radioactivity. All right. So decaying radioactive something makes heat. What is it that's decaying, Liam? Isotopes. All right. What's an isotope?
It's an
Wait a minute, hand. What's an isotope? Okay, Alex.
It's an atom of an element with a different number of neutrons than normal. Oftentimes unstable.
Yes.
Sometimes it can be perfectly stable and it's just slightly heavier.
Mhm.
But most of the time, it's gonna try and kill you.
Could be, yes. So yes, it has a different number of neutrons, which means its mass number is different, right? Because there are only two parts of an atom that really contribute to the mass. It's mostly the neutrons and then a little bit the protons. The electrons don't contribute to the mass. Now, an element that is missing or has gained an electron is not an isotope, but anybody, Joseph? An ion, right? Does anybody remember what a positive ion is called, Jack?
Wait, no, no, I know the answer.
Okay, wait, I'll do the, you can do the negative. Bailey, what's a positive one? A cation, how do you remember that?
Yeah.
It's positively adorable. And then the negative one, why?
Because it's like an onion, it makes you cry.
Yes, it's sad, it's negative, right? Okay, that's how you remember. Very good. I love little stupid things that make you remember, because you'll never forget that one. You'll be 50 and know the difference.
Well, I did just forget.
Yeah, well, no, but you knew, like you knew. So yeah, so here's an example. As this parent isotope decays to become the daughter isotope, it will create heat. That's because it's what do we call this sort of thing when an element or a molecule or something happens at a chemical level and heat's produced? Do you know?
Exothermic reaction.
There you go. Okay, so it's making heat, right? All right. So that's important to remember. All right. Now, asteroids and meteors. What creates, what do we want here? We got asteroids and meteors. What do we think is going in this blank? It's creating heat. It's not that hard. Yeah. Okay, so yeah, asteroids and meteors create heat. Why? Why are they creating heat? Oh, Parker, you why? Why are they making heat? Do you know? Yeah, you look like you weren't quite there, so I'm checking in with you. You don't know, Drew.
This is actually something that people have experimented with. I'll say that.
Uh-huh.
But you have lots of meteors
Mhm.
in the air,
Mhm.
they're like really hot.
Yeah.
They're flying through the air, they can actually heat up the atmosphere to really hot.
Yeah. Why are they hot though?
That's actually exploded every new thing in the world, and then the world would be like an oven before they even hit the ground.
Well, why are they hot?
Why are they hot? Because there's lots of friction.
There's friction in the atmosphere, right? They're passing through a fluid, which is certainly going to be less friction depending upon the viscosity of that fluid or the density of that fluid. And the air is not all that dense. Our atmosphere is not all that dense, but they're shooting through our atmosphere. That's creating heat. That's why we see the light, right? What happens when the space shuttle, for example, or a capsule returns to the atmosphere? What happens to it? What are you going to say, Caitlin?
It catches on.
It does, correct. All right, so it catches on fire pretty much, right? Do you guys remember? No, I don't think you were born yet. Space Shuttle Columbia was, I think, right before you guys were born. So Space Shuttle Columbia, upon re-entry, caught fire and exploded, unfortunately, and we lost the entire crew. And the reasoning was that one of the tiles on the exterior of the space shuttle, which are insulating tiles, there was a gap and it had come off during launch. One tile.
Yeah.
It came off during launch and they didn't even notice it really. Like when you look back and see it, you can see it. But they were on their way in and they caught fire and exploded on the way into our atmosphere. And I remember it because we'd just gone taking the dog for a walk in the park and we were listening to the radio and then there it was. It was like, oh my goodness. What were you gonna say?
They actually noticed, but it was too expensive.
Yay. Yeah. Can't remember the whole story behind all the details, but yeah, it was nuts.
That picture was like must have fallen.
I don't know what it is. It just looked cool. I thought, oh, that works with my background. I'll use that. I'm thinking about the images. I really am. Like it has to look right. So anyway, yeah. So obviously we're creating heat. We got lots of friction. We got stuff flying into the atmosphere. So that's how Earth got warm. All right. We got radioactive decay. We've got gravitational contraction. We've got asteroids and meteors flying through the air. So now we're warm. Now we can't stay that warm forever because that would be crazy. So it had to start cooling. No, we wouldn't be here. No. Yeah, it would, this would be Mars or something, or not Mars. Yeah. Mercury or Venus. Yeah, one of them. So Earth cooled enough for what to form, Chloe? Crust. Anybody want to give another one, or that we going with Chloe's? Bacteria? Is that what you guys, is that what you said? I couldn't hear you. Cold enough for bacteria. Yep.
Oceans.
Oceans, Alex.
Ice.
Ice, and Caitlin.
I was gonna.
You're gonna say water. We're looking for water. So yeah, so Earth cooled enough for water to form after 200 million years. The atmosphere is still cooling today. Now, when we get into our space unit, which is the second to the last bit of this class, and then we talk about it a lot more in physical science too. We talk about how we know for a fact that the universe is expanding. And does anybody know the scientist that whose law it is we use to describe, we use to explain how we know that the universe is expanding? Do you know?
I don't know the scientist, but I do know it's the redshift.
It is redshift and green shift. Yeah. Do you know who it is?
Doctor Strange.
That would be amazing. Well, I named my new fish. If you didn't notice, he has arrived. Isn't he gorgeous? I named my new fish after that guy, who also has a massive satellite with a gazillion mirrors on it named after him. Edwin.
Hubble.
James Webb.
James
That's not Webb. That's a good one. You had it. Edwin Hubble. Yeah. Hubble.
Right?
So Hubble's law is that he's the, you have to get Hubble. Yes. So Edwin Hubble. Yeah, he's the one. We'll talk about him some more. But he's the dude who helps us understand the fact that everything is still moving. So there's still effects from this whole beginning of things. Our atmosphere is still cooling. So so this kind of sums it up. Why do scientists theorize that the early Earth was hot? Can we summarize them all? Drew. We just went over like some real, give me a specific one. Well, no, give me a specific one. We just went over a couple. James. James, you give me one.
The answer is
Formed from gas. Yep.
meteorite bombardment.
Meteorite bombardment. That's going to be one. All right. Anybody else? Parker. Well, we didn't have water. Yusuf. Gravitational contraction. That's a big one. Okay. Lily, do you remember any of the others? We just talked about them. Gravitational contraction. Then we had lots of warm, hot things. And then other things that oh, those too. We had these things that decay and produce heat.
Yeah.
Good.
Decay and hard 4.5.
I was gonna say if guns produce heat, I want my money back. I mean, if guns decay, I want my money back. But they did produce heat. You're correct. All right. So what we're looking for is, gravitational contraction, meteorite bombardment, radioactive decay. These are the things that made for this hot, inhospitable Earth. Okay, formation of the crust and continents. So Earth gets crusty. So Earth's earliest crust likely formed as a result of the cooling in the uppermost mantle, because now think about this. Think for a minute. We've talked about the temperatures at which rocks melt. All right, you're talking about an Earth that the top layer was still liquid. That's how hot it was. That's crazy. So once it starts cooling enough that some of this starts to kind of cool down, this is almost like you can picture your pan of tomato soup. You know, I got that skin on it. Same kind of deal. All right. So Earth's earliest crust. So we have something, and what's this here? Do you know what we want here, Liam?
Differentiation.
Differentiation. Very good. All right. So differentiation. So internal zoning of a planet from materials settling in layers due to variations in relative density. Most dense at the bottom, least dense at the top. Okay, you got a bunch of stuff spinning around in space, bunch of elements, some compounds that have slapped together, and they're all getting squashed to the middle. Obviously, the most dense things are going to go to the center. Okay, it was almost like if you took a tube, okay, and in it you had in your hand glitter and marbles and I don't know, little tiny lava rocks, and you dropped them in. You would expect the marbles to hit the bottom first, right? Then your lava rocks and your glitter would eventually settle. Same concept, okay? It just takes a while. And we call that differentiation. And it's not just Earth, as you can see. Venus, Mars, Mercury, and the Moon all have internal zoning or differentiation.
Just like my humans, I prefer tomato soup without the skin.
Have you seen Silence of the Lambs? Oh, or what are these other movies that are... You're a little frightening sometimes, man.
Yeah, uh-huh.
Good.
Hang on, wait a minute. Caitlin's talking. Say it again.
This tastes like chicken.
I don't want to find out.
Tastes like chicken.
Mm-hmm.
What is steak?
I was about to say, has anybody in here ever eaten anything that is like atypically weird? Have you eaten snake?
I've heard.
Have you? What have you, Lily? You've had snake? I've had snake. How about you, James? Alligator jerky. I've had alligator, yeah. Uh-huh. Deer, yeah, yeah. So snake, where did you have snake, Lily?
Oh, so when we used to do like summer camp,
Uh-huh.
anything,
Oh, no.
and laying the counselors.
Yeah.
So one time when they were heading out to do like I think it was zip lining,
Mhm.
huge copperhead
Ugh.
was like attacking one of the kids.
Yikes.
So obviously he had to kill it.
Right, yeah.
It was gonna
At that point, yeah, you kind of have to.
brought it home and my dad they de-skinned it and then he grilled it up and we ate it
How did it taste?
like
Chewy chicken. So when we were in China, we went to the black market, which is this thing, or the night market actually is what it's called. It's if you've ever seen the pictures of the Chinese people like late at night and they have these carts and they have weird stuff like cockroaches and silkworms and scorpions and people eat them. And the craziest thing we got was snake, but it was a little snake that had been rolled up like in a little
Like a
concentric
kebab?
circle. No, like a lollipop and then stuck on a stick like a snake pop.
Oh.
And so we tried it. It was really greasy and kind of like a cross between a chicken and a fish. Don't recommend. So yeah, we had some bread. It wasn't even good. It was kind of pita-ish. It was more like what is it, bubble pancake, but
Yeah.
but it had like it was not good. It wasn't scallion. It was like weird black sesame seeds. So yeah, cockroaches and yeah. So Earth's earliest crust. All right, so we go from this to this. So Earth's earliest crust first formed at least how many billion years ago did we start getting crust? Anybody want to throw a guess out there, Drew? 200 million? What do you think? 4.21? Yeah, Alex, guess?
I'm gonna guess like 4.4, 4.5.
Okay, Liam?
3.1 billion.
All righty, Piper? You had one, Parker. What are you going to guess? 100 million. And I'll take my last one there, Bailey. Wait, what'd Bailey say? 4 billion. All right, so 4.4. So I think, here we go. We had a couple winners that were real close there. So 4.4 billion years ago. And then that's just how many years after the formation? Do your math. Do your math. How many million? Was in the last slide, Liam? 100 million? Yeah, it was about 200. That's 160. The last slide said 200. This slide says 160. Again, we got to estimate, but when we're talking about numbers that huge, remember we talked about how huge it really is. Yeah, you got a range and that's probably going to be good enough. So likely this kind of crust was most similar to the ocean. What do we have at the ocean? Yeah, do you know? It's oceanic crust. What kind of crust do we have there? Does anybody remember what it's composed of, Liam?
Sediment.
Sediment? Alex, do you want to guess?
I thought it was basaltic.
All right, here we go. So it's basaltic. Alex, again, you're having a day, man. So yes, it's basaltic. That's what we're thinking is there. All right. All right. So then we had our early continents. Jeez, man. Something about D&D. What now?
Get sugared up and play at GGC tonight.
Ah, okay. So you won't be home, basically, is what your sisters want to know. Oh, sorry. This kid and sugar is the thing. All right, so back on topic. All right, so what do we call a small piece of continental crust?
A sandwich.
Piper. Hang on, Piper. I called Piper. Yeah. Yeah, I just have to take him at 3:30.
Okay.
Yeah. Okay, Caitlin. Microcontinent. All right, that's what it is. A microcontinent are these itty little guys, and they squash together to form bigger things. So what was the ancient continent that formed the core of modern day North America, Drew?
Pangea.
Pangea. Anybody else want to throw another one out there? Bailey? Laurentia, and you want Laurentia? All right, so it's Laurentia. All right. But we also called this the North American craton. All right. What's not a crouton?
No.
I know you put croutons on soup sometimes, but no, we're back here. Craton. Anybody know what a craton is? You know? What is it, Yusuf?
Most stable part of the continent.
Most stable part of the continent. All right, oldest, Caitlin.
Buried and exposed parts of the shield.
There you go. All right, so yes, what we got is your stable interior, basically what he was saying there, and a portion of the continent characteristically composed of ancient crystalline basement rock. Basement rock, this sounds like a band. Sounds like a garage band or something, basement rock. But obviously we're talking, yeah. We can't really call it bedrock because it's deeper than that. All right. So the craton, here it is, the North American craton. So the buried and exposed parts, this is what Caitlin was getting at, of a continental shield together compose the craton, the stable core of a continent. So some of it's buried, some of it's under the ocean, right? But then the whole thing together is the craton. So then you have these different shields. You have a Precambrian shield and a Canadian shield that are over here as part of our, if you look back here, our North American craton. So which one is this? It says, so these are nuclear as in beginning areas of Precambrian rocks present in each of the continents. So which shield is a continental core of Archean and Proterozoic rock? All right, Yusuf, do you know this one?
Precambrian.
The Precambrian shield. Okay, and let's see. Boom. All right, so the next one is going to be, Liam, the Canadian shield. So the Canadian shield, is the Precambrian shield specifically in North America. So the Precambrian shield covers more than North America, but when we're talking about it as specifically in North America, we narrow it down to the Canadian. All right, so the formation of atmosphere and oceans. So Earth gets itself a sea and a sky. So evidence shows that oxygen existed in the atmosphere during the Proterozoic, which is Earth's early, and that Earth's earliest atmosphere was composed mostly of hydrogen and helium, which was eventually replaced with oxygen, nitrogen, carbon dioxide, which is what we have now. So we're talking about this back in the beginning to this today. All right, so let's think about it for a minute. First, let's look at how it changed over the years. So Earth's early atmosphere was full of, this is what? Together, hydrogen, and this one is?
Helium.
What is hydrogen's atomic number? 1, and helium's is? Yes, now by the way, this is a weird font issue. Why?
Because
The E should not be capitalized, correct. So it's a weird font thing, it shouldn't be capitalized. So asteroids brought some water to Earth, we believe, comets too, right? And volcanoes are gonna produce other gases. What's one of the main gases that comes out of volcanoes? Jack, do you know? Whoop, that wasn't the question you wanted to answer. He's gonna take a guess.
Water vapor?
That is one, this is true, Drew. Carbon, carbon dioxide is what I'm looking for. And that's important because in a minute, you're gonna see how that all kind of goes together to get us where we are today. All right, so you can read this. Why was the earliest atmosphere eventually replaced by oxygen, nitrogen, and carbon dioxide? Who can explain to me what happened there? All right, Liam, can you explain it?
Volcanic outgassing
Okay, and that, what does that do? That causes what?
causes the
You got it.
gases to like go out of the volcano.
Okay.
Smoke up into the atmosphere.
And smoke up into the atmosphere. That's a good way to put it. All right. So basically what we have, oh, Drew, did you have something to add really desperately? Oxygen, nitrogen, carbon dioxide? Yeah.
I was
Where?
gonna say
Uh-huh.
the ocean.
Oceans. Okay. So these are the big 3 that we have now. There's this whole process where it's like step after step gets us to step. And it makes a whole lot of sense. So we're going to go over it kind of piece by piece. But hydrogen and helium can't hang around for long in this atmosphere because they have very small masses. We talked about this, 1 and 2. Basically, like how many neutrons does hydrogen have?
2. Or hydrogen.
Hydrogen, yeah, it doesn't really have any, right? It's got a proton and that's about it, right? And then we think helium has like, maybe one. So two. So both helium and hydrogen have small masses. So Earth's gravity was not great enough to keep them from just floating off into space because they have very low density, they have very low mass, and you got gravity pulling, but they're so light. What happens when you let go of a balloon full of helium? Okay, same thing's happening even if it's not encased in latex, right? It's still floating up in our atmosphere. It's currently floating up, right? So it can't keep them from taking off into space. So gases with higher masses like carbon, nitrogen, they're unable to escape Earth's gravity and they've eventually replaced the helium and the hydrogen. It's just a displacement thing. Your stuff with the higher mass is going to get pulled towards the center of the Earth always. And your stuff with the lower mass is going to get pushed up. They're not floating. When you let go of that balloon, it's not floating up so much as the air around it is pushing it up because it's trying to get underneath of it.
Out of the way.
Convection. Okay, yeah, kind of, sort of like that, except it doesn't really, doesn't come back down as much. So let's look at these. Okay, here are our masses. Here's our numbers, and here are our masses. What's the atomic number? Where do we get that from? These ones at the top. Where's the atomic number come from? James? Random neutrons in the nucleus. Anybody else want to guess? Give me a guess. Give me a guess. Jack?
Number of protons
Number of protons where?
in the nucleus. No, in the. Thank you.
You're good.
I noticed.
You're good. All right. So you're just waiting because you didn't sound sure. So yeah. All right. So your atomic number up here is your number of protons. And yes, your protons live in the nucleus. And your atomic mass is the number down here. And it's basically the masses of your what and what? We said it? Yeah. Go ahead.
Protons and neutrons.
Your protons and neutrons together. Okay. And you consider that you give a proton about 1 and a neutron about 1. So this makes sense. This number makes perfect sense, right? You'd have 12. All right, see how much more mass these have than these dudes here. And why does this say, something else to keep in mind is that you'll see as we work through this here, that not all of these elements are ever hanging out alone. For example, there's a typo that should say molar, and I bet it's going to say it 100 more times because I copied and pasted. So yeah, molass. Well, the molar mass of a hydrogen molecule. Okay, so a hydrogen molecule is not one hydrogen atom, it's 2. It's one of those ones that always has a buddy. So how do you find your molar mass? So a mole, can anybody explain a mole? Anybody want to give it a shot? Anybody who's done chemistry with me? Bailey, you want to give it a shot? It's kind of hard to explain. Avogadro's number is what we use with moles. You're right. Okay. 6.4 times 10 to the 23. So yeah, so a mole is like, it's an amount of something.
It's one Avogadro's number.
It's one Avogadro's number of something. It basically, for things this small, for atoms and whatnot, we have to give them like a quantity that we can measure them by. And that's what a mole is. It's an amount. And basically what it's for is comparing. So like 1 mole of hydrogen reacts with the same amount of oxygen, and your proportions stay the same. It has to do with ratios and proportions a lot. And when we do chemistry 2 more years from now, if you're still around, we'll do a lot of stuff with moles. So the way we figure out molar mass is we say grams per mole. So hydrogen, its mass here is 1, see, 1 basically. So it's 1 gram per mole plus 1 gram per mole because there's 2 hydrogen. That's 2 grams per mole. So here goes molas. I'm going to have to fix this. So the molar mass of helium. Does anybody want to guess about helium? Hydrogen is going to be 2 grams per mole because there's 2 hydrogen together. So what would helium be? Anybody want to guess?
4.
4? Anybody else want to guess? Yeah.
3.
3. Say it.
5.
2. All right. So helium always hangs out with another helium. So that means you're going to have 4 grams per mole plus 4 grams per mole, usually does, typically, when it's free. So you get 8 grams per mole. So you got 8 grams per mole, 2 grams per mole. Okay, now we're moving on.
Helium hangs up with another.
Usually hangs out with something else. Yeah.
But, you know, valence shells completely full.
Yeah, I'll get you a graphic. There's a graphic somewhere that I saw when I was putting this up. So if you do the molas mass of nitrogen, what are you gonna get there?
28.
28. Anybody else?
Because I know for a fact that one hangs out in groups of 3. No, in groups of 2.
It hangs out in groups of 2. And so you're gonna get 28. That's right. Now oxygen, we all know this by now because we've said it a couple times. Is oxygen alone or does he have a buddy?
Ghost. Buddy.
Oxygen is always with the buddy. So we're gonna get 32. And then this is important. Oh, that should not say that. What does that say? It meant to say carbon dioxide. Okay, carbon dioxide, which is the other gas we're talking about up here, right? That shouldn't say oxygen. So what are we gonna get for carbon dioxide? We have a 12, 16 and a 16.
44.
Math man saying 44. What do you get? 40. Yep. All right. So we're going to get ourselves 44 gram per mole. And so now you can see these dudes are remarkably lighter than these dudes, right? 2 and 8 barely compare to 28, 32, and 44. So they're going to get pushed out of the way as the other guys come down. All right. So outgassing, which is what Liam mentioned a minute ago. So this is where you have to follow. It's like follow the steps and it makes sense here. So the process by which volcanoes vent water vapor, as Jack mentioned, carbon dioxide and nitrogen and other substances is called outgassing. Oh, look, it's exploding. That's fun. All right. So carbon dioxide is coming out. This is important. Now we have a source for carbon dioxide in the atmosphere. We have to have that source. And here's why. Because we have our cyanobacteria. Cyanobacteria are blue-green algae, basically. All right, and they're tiny little guys like this, and they are thread-like and photosynthetic. So now we have carbon dioxide in the atmosphere thanks to the volcanoes. And they're photosynthetic. So they're going to consume that carbon dioxide, and then what are they going to do? Liam, they're going to basically, yeah, they're going to breathe out oxygen. So now we have oxygen. So thanks to the volcanoes, we have carbon dioxide. And because we have carbon dioxide, we have cyanobacteria. And thanks to the cyanobacteria, we now have oxygen, okay? We're getting somewhere. Does anybody know what these are called? Do you recognize these, Yusuf? Yeah, that's a fun one, isn't it? Stromatolites, okay.
Sea turds.
So, yeah, so these are fossilized, basically, but there's still some that are living, very few living examples. But what they are is there's this big mat or mound that contains billions of these blue-green algae, right? And now they look like this, or like this, where you can really see it. But this is Earth's oldest living life form, and some of them still exist. So it's Earth's oldest life form, and some version of it or descendant of it still lives, just very, very few of them. All right, so we had volcanoes that gave us carbon dioxide, right? Carbon dioxide was consumed by cyanobacteria, which then produced oxygen. Okay, we've got carbon, we've got oxygen, we're getting some carbon dioxide and oxygen, we're getting somewhere. So there's stromatolites here. So they produce the first, what were we just saying? Oxygen. Okay, and you need that to build an ozone layer. Okay, now our ozone layer is up in our atmosphere, right? And it's not 1 oxygen or 2 oxygens, it's O3. Okay, now this is an interesting little graphic here. These are images of the ozone layer from 1979 to 2022. And does anybody know what the big deal was with the ozone layer in like the late 80s? Do you know, Bailey? Oh, you took a bite. I always call people when they take it. I'm like a waitress. How's your food? You know, they wait till you put your fork in your mouth to ask you how your meal is. I swear they do it on purpose. Yeah, okay. There is a hole in the ozone layer. Alex, turn around. Yeah, all right. So there's a hole in the ozone layer. Oh, look, it's still there. And you can see it started like this, and then it got like this. Okay, so this is a pretty quick growth. So the hole in the ozone layer has been blamed on chlorofluorocarbons, CFCs, which are, yes, propellants. Okay, but you can also get them from natural things. Does anybody else know where kind of like some of these same chemicals reside? Do you know?
Cows.
Yeah, what were you gonna say? Bailey? I did it again. I love it. Oh. What were you gonna say? Counterparts. Okay, so we've got,
Rectal passages of.
okay, we're good. All right, so yes, cow farts. All right, so you get these chemicals going up into the air. Now, cows and animals have been around and they've been passing gas and breaking wind forever. So why suddenly is this large amount of it being produced? Well, that's farming, mass farming, places where we have hundreds and hundreds and hundreds of cows, specifically for mass slaughter for grocery stores. That's different than the way it was before, where you had, like, you know, your small town farmer and he'd whack up a couple cows and hand them out to the villagers and they'd trade him whatever. It's not the same thing as mass commercial farming, right? So there's that, and then there's CFCs. Now, y'all remember, if you've ever seen any pictures of your parents from the 80s or anybody else, we had, you know, we had the hair, you know, like this, you know, it was real big. Mine was awesome. And that is thanks to some amazing hairsprays. In particular, anybody know the one that we all loved and then they had to ruin it? Aquanet. Everybody heard of Aquanet? Aquanet was the jam. Yeah, Aquanet. But it was, so they took those CFCs away and then everything became pump for the longest time. And you could watch everybody's hairstyles change because you just couldn't do it anymore. And then that's part of it. I swear that's part of the reason culturally why we had a fashion switch. And then they came back and found other ways to propel stuff. Asthma inhalers were affected. Lots of things were affected. But as you can see, it's still there despite a lot of these restrictions. And look, it kind of shrunk up and then up, kind of moved again. So again, natural process, human intervention.
Kinda both.
Yeah.
kinda stuff.
Liam, were you gonna add something?
I heard about this country that they were taxing cows for their burps.
And not surprising, that sounds like something we would do. So well, don't get me wrong. So now we have, since we have an ozone layer, we have UV protection. What were you gonna say, Milo?
Speaking of stuff that the US would do, NASA is spending its time by running a program to see what would happen if a giant marshmallow hit a
Not surprising.
Pay your dollars well.
If you want to see weird, a really weird list of government spending every year, Senator Rand Paul puts out his annual Festivus. He does it on Festivus, the holiday of Festivus. He puts out a whole list of government wasteful spending, and it's stuff like that. I remember a couple years ago, it was a study on how long it takes to catch up to poor, and they did stuff with, like, I mean, it's some of it's just bizarre, but that's how you get grants, you know, that's how it works.
And that's our
So we had volcanoes that produced altogether what? Carbon dioxide. And then we had cyanobacteria, which came along and it consumed the carbon dioxide and made what? Oxygen. And the oxygen went up and created an ozone layer, which gave us ultraviolet protection. This is a big deal. We can't live without UV protection. So then we have banded iron and red beds. Okay, so this is how we know when we got oxygen. So iron oxide is rust, right? Iron on its own is not red, but if it comes in contact with oxygen, and especially if it's like nice wet oxygen, you get rust, right? So iron oxide formation is evidence of the presence of atmospheric oxygen.
That's why.
So we have sedimentary rocks that are younger than 1.8 billion years, and they're colored by iron oxides in them, and they formed on a land in an oxygen-rich environment. And we call these red beds, okay? And then we have this. And this is a deposit consisting of alternating bands of chert, which is a type of mineral, and iron oxide. And it's underwater. And what are these? Yep, these are banded iron formations. And they're formed underwater in an oxygen poor environment. So we have these two types of evidence of atmospheric oxygen, because you wouldn't have these without it. So if you can date the rock and know that it has iron oxide in it, then you know what date we had oxygen. So then, because we now have oxygen, we can have respiration. So respiration and photosynthesis, how would you characterize these two processes? Respiration and photosynthesis. Oh, Lily, you know this one. Respiration, photosynthesis. What are they to one another? You know it. Yes, you do. Plants take in oxygen, breathe out carbon dioxide. Animals breathe in oxygen, put out carbon dioxide. So the processes are, you know it.
Oh.
It's easy word. No. They're opposite, right? Okay, they're opposite. Ah, she's like, why? Yes, they're opposite. So there's actually, it's more complex when you start looking at the whole process here, where you've got cellular respiration and you got Krebs cycle and light independent and light dependent reactions and all this business. But your big overall picture is that you get solar energy put in, and that is photosynthesis. And when you're putting cellular respiration, the energy coming out is heat, or ATP. So now we've got atmospheric oxygen, source of the source of the atmospheric source of oxygen is important because it allows for respiration. So we had volcanoes that gave us carbon dioxide. Carbon dioxide allowed for the evolution of cyanobacteria, which then breathed out oxygen, which we can prove because we see it in banded earth and in banded formations and in red beds. And then we now have oxygen, so we can have respiration, which means we can have all of these other types of animals. So the oceans now are going to form as liquid water formed, heavy rains fell, filled the low-lying areas, and as runoff traveled to the oceans, it dissolved rocks, and those dissolved minerals made the oceans like what, Liam?
Salty.
They are so
Salty.
salty. Yep. Yep. You know, when you go and you accidentally get some of the ocean water in your mouth when you're swimming in it, it's very salty, right? And some are saltier than others. But now we have water. So we have water and oxygen. So we really can have life. So now we've got the opportunity for a whole bunch of life. So we've got, what's our origin? What are our earliest things? So the earliest known life forms on Earth are believed to be fossilized microorganisms found on hydrothermal vents. And these are within their precipitates that come from the hydrothermal vents. Where do you find a hydrothermal vent? Milo. Yeah, anywhere like that. Deep ocean trenches, anywhere like that. Anywhere where you've got, like, you know, basically venting from deep in the earth. And we think that these organisms are about 3.42 billion years old. So one idea, how did it get here? We got a bunch of ideas. All right, so we have this idea called primordial soup. You've probably heard this before, right? All right, so the belief is that we have these three types of molecules, and they're in Earth's early atmosphere, and they can, when under the right conditions and in the presence of electricity or lightning, combine and form organic molecules, which means they contain carbon in their life forms. And we what?
Lightning's misspelled.
Oh, good one. All right, I got one. I'll put it up here.
Lightning,
So
not lightning.
that's one I always do wrong, and I didn't catch it. And actually, I think I copied that. Anyway, it's been replicated successfully in the lab by these guys, Miller and Ulrich. What are the three elements, or three molecules, sorry, that we're looking for? Okay, Caitlin, I'll take you. Give me three.
Hydrogen, ammonia, and carbon dioxide.
All right. Hydrogen, methane, yeah, which is not that chemically different, and ammonia. So yeah, count for it. So we get these together, and we have this experiment here. So Miller and Ulrich believe that during the Archean period, Miller and Ulrich demonstrated that the basic building blocks of life were mostly present. Yeah.
I think it's missing the L.
Oh, where? Oh, Ulrich, you got another one. That's two. All right. Finding them today. Is it? Oh, that's weird. Or maybe it's not Ulrich. Maybe it's Yuri, and I'm getting it wrong. I think it is Yuri, and I'm saying it wrong.
So the first one was on.
Oh, I don't know. No, I gotta check. I thought it was Ulrich, but I have a friend whose last name is Ulrich, so I may be confusing it. So this is what they did. They had heat, cyanide, certain clay minerals, and they caused amino acid chains to form. All right, so let's watch this one.
And now it will take it away.
Life is absurdly complex, extremely specialized, and somehow we haven't found it. So we must have just gotten really lucky, right? Maybe not. Well, you lively bunch, Julian here for D News.
There are a lot of ideas to explain the origin of life on Earth. There's panspermia, the idea that life took a cosmic hitchhike and crashed into our blue dot 4 billion years ago. There's primordial soup, which hypothesizes that when you take ancient Earth's chemical conditions and add a dash of lightning, you can turn inorganic precursors into organic compounds. Sounds crazy, but the Miller-Urey experiment.
Urey, that's right, it was right. I said it wrong, so brownie point.
20 amino acids, the building blocks of protein. But now there's been a new idea put forward that's so simple, so elegant, so novel, it might change everything we know about life and where it comes from. Jeremy England, a physicist at MIT, has proposed that life is something that matter just does when exposed to an external energy source like the sun and surrounded by a heat bath like the ocean. It sounds like a cop-out, but there's math behind it. England's hypothesis operates on the second law of thermodynamics, which states that as time passes, the total entropy of a system increases until it reaches thermodynamic equilibrium. That in English basically means that systems dissipate energy until it's equally distributed. Entropy is often equated to chaos, that isn't quite right, and saying that to scientists will make them laugh at you. At least that's what Tricks tells me. Anyway, when going by the entropy equals disorder misconception, life seems like it violates that law of thermodynamics. Living things are orderly and organized, though I can never seem to find my wallet. But because living things dissipate energy in the form of heat, we're actually adding to the overall entropy of the universe, and thus the second law is conserved. According to England, atoms actually form organic molecules and eventually life because it's naturally a more efficient way to dissipate energy. They have to be getting that energy from somewhere and be surrounded by a bath like an ocean or atmosphere to dump heat in, but that's exactly like the conditions on this new place called Earth. This also supports why life reproduces. Reproduction makes more compounds that dissipate more energy. Therefore, when natural selection is applied, successful life forms should waste as little energy as possible reproducing, but should still be above the theoretical minimum. When England looked at E. coli in 2012, he found that the bacteria operated just above this minimum floor of waste heat. England's math checks out, but whether or not it's why life came to exist is still up for debate. Currently, experiments are being formulated to test the hypothesis, but even if it turns out to be a non-starter, England's novel idea will tell us a lot about a question we've been asking for millennia. There are a lot of really interesting ideas of where life comes from, and we still have no conclusive scientific evidence for one or the other. Anthony's got a great bit on primordial soup in this video over here. All right, guys, I can already hear those fingers flying.
So we have the primordial soup idea. Now we've also got this new guy that he brought up, England, who has this whole entropy idea. So the basic idea of the primordial soup, though, is that some of these organic molecules produced at hydrothermal vents were what? What do we call the building blocks of proteins? Liam? Amino acids. All right, these are the building blocks of proteins. All right, now this gets interesting. Amino acids are molecules that combine to form proteins. Amino acids and proteins are the building blocks of life. When proteins are digested or broken down, amino acids are left. And if you remember when, back when we did DNA and biology, if you were with me, you've got all these nucleotide bases along a strand of DNA, 3 of them at a time is called a codon. When your RNA comes along to produce the protein, it sees those 3 and it goes, okay, which amino acid is that? And it pops one of these guys in and goes along to the next one and then adds another one of these guys. And it keeps doing it until it makes a complete protein, which then balls up on itself like a little knot, right? So this whole idea is that some of these amino acids can be produced at these hydrothermal vents. So some of these organic molecules are building blocks of proteins, and when other gases present at Earth's formation, like carbon dioxide and water vapor, are combined with lower levels of hydrogen, methane, ammonia, amino acids do not form in high quantities, so there's really not sufficient evidence to totally support this theory. That's going to be the case with all of them. So at your hydrothermal vent, that's your hot water at the volcanic seafloor rift. There's a good picture of one. Woo, very cool. So then we have amino acids, though, that have been found in the waters of hydrothermal vents. So we suggest that, you know, proteins and nucleic acids are what make up DNA and RNA, right? Nucleic acids, they could have formed as early as the Archean. So how do you get cells then? Because cells are your basic unit of life. This guy's kind of dry, but
2.8 billion years ago, and much is still shrouded in mystery. We know, based on the geological record, that life
sounds like he's asleep.
Sounds like he's doing it like this.
Listen though.
Scientists have created the molecules of life in the lab by blasting simple precursors with radiation or stimulated lightning. Amino acids, sugars, nucleotides have all been created under artificial conditions, attempting to mimic the early Earth environment. Wait a minute. What's the point in creating these exotic molecules of life if they're not interacting with each other in useful ways? They could all be swept away by the next wave of wind dust. The molecules of life must be kept together in a confined space to do the things that living cells do: create proteins, undergo metabolism, reproduce. All life forms have a barrier, a cell membrane. It is the most fundamental component of living systems. After 2 billion years, gargantuan cells, the eukaryotes, evolved, which gave membranes within membranes, compartmentalization, making many cellular processes more efficient. Another billion years and multicellular systems emerged, but the cell remained the single irreducible entity of every living thing. How did the cell structure originate? First, let's understand what a cell membrane is. A cell membrane is composed of a lipid bilayer with water on the inside and outside. It is thought that the earliest life forms made membranes from single-chain amphiphiles. An amphiphyle is hydrophilic at one end and is most stable interacting with water. At the other end is a hydrocarbon chain, which is lipophilic or oil-loving. The amphiphiles spontaneously line up so that the lipid ends are away from the water and the hydrophilic ends are exposed to the water. Under the right conditions, these will form protocells. It has been a puzzle how amphiphiles formed in the early Earth and made protocells, but new research has shed light on the answer. To understand, we have to plunge into the ocean depths of the early Earth, deep, deep underwater.
He's awake now.
At thousands of meters underwater, alkaline hydrothermal vents spring up at the rifts, dividing tectonic plates, where ocean water seeps into the Earth's mantle and then is released from vents at high temperature and pressure. The expelled alkaline water deposits mineral-rich chimneys up to 60 meters tall. With a
that auto?
ventilator, the surrounding seawater and the mineral deposits come together is where the chemistry takes place that may hold the answer to the origins of life. The fluid flowing out of the vent is divided by the surrounding seawater by a thin layer of iron nickel sulfide-rich minerals, which are crystallized, forming the vent chimney. The vent fluid is hot, it is alkaline, and it has high levels of dissolved molecular hydrogen. The surrounding seawater, on the other hand, is cold, acidic, and has high levels of dissolved carbon dioxide. This arrangement creates an electrochemical reactor in which hydrogen and CO2 react. The hydrogen serves as a reductant, donating electrons to carbon dioxide. The mineral layer acts as a semiconductor, shuttling electrons across the interface. The reduction of carbon dioxide forms formic acid, which is the starting point for the creation of lipid bilayers. This process has been duplicated under laboratory conditions. Under the high hydrothermal vent conditions, the formic acid decomposes to give carbon monoxide. The components will react, catalyzed by iron, to the single-chain amphiphiles, giving both fatty acids and long-chain alcohols in various chain lengths. This process has been demonstrated in the lab, which mimics the conditions of hydrothermal vents. The amphiphiles will line up to give their most stable configuration and form lipid bilayer structures. It has also been shown that the conditions of the hydrothermal vents, namely high pH and high salt concentration, favor the
No, whatever. We were almost done. It was almost over. So you can finish that. I'm watching the time. So you can finish that one at home. That dude is sleepy, but he's very thorough. So how do we get these amino acids? So some people don't think they came from hydrothermal vents. Some people think they came from meteors. That's right. Scientists did confirm in 1971 that the Murchison meteorite contained amino acids, primarily glycine, and that those organic compounds likely came from outer space. In decades since, amino acids and other chemical precursors to life have been uncovered in other fallen space rocks because it's always aliens, right? Always aliens. So where do they come from? Do they come from hydrothermal vents? Do they come from the alien guy? So was life planted on Earth? This is yet another theory. Okay, let me see. Okay, I think we may, how long was this one?
Today,
We
Rock 84
to watch a little of it,
41
but I'll have to come
speaks
back to it
to us
later.
across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered.
These were the words by President Clinton when he unveiled the rock Allen Hills 84001. The Earth was formed 4.6 billion years ago. For millions of years, it stayed dormant with no form of life appearing. And then around
So
3.5
watching the
billion
time,
years ago,
we'll skip ahead, but know that there's another video you can watch there about where they come from. So what if they didn't come from the hydrothermal vents? What if they came from space? Well, here's another idea. A new study finds, and this is not even the study with the, remember we have the entropy guy too. That's another one, all right? Then we have this one, amino acids, they come from the sea. A new study finds that when certain rocks below the seafloor, interact with seawater, they undergo serpentization. Okay, they can create amino acids. These serpentizing rocks are commonly in the early crust and may have provided the chemical precursors that formed before the origin of life. So serpentization basically is hydration, which means you're adding a water molecule to something, and metamorphic transformation of ferromagnesian minerals. So this is stuff like olivine, pyroxene, mafic and ultramafic rocks is where you're going to see this. And minerals formed by serpentization include the serpentine group, which is things like antigerite, lizardite, chrysotile. I love that one, lizardite, and brucatite, talc, and all these nickel iron alloys, all this other stuff. So mineral alteration is particularly important at seafloor and tectonic plate boundaries. So now we've got alien dude, we've got hydrothermal vents, we've got serpentization, and then we've also got the new guy who came up with entropy idea in that first video they mentioned. I'll leave you guys to watch this British dude who is really excited, or maybe he's Australian, about these serpentized rocks. This green, these are these serpentized rocks here. Now I know why it's called so green like a snake. He's very excited about them. That's where you find them. And then that's just a little GIF. There you go. So amino acids, come here. So RNA may have been the first replicating molecule on Earth. And that's just, there's RNA doing what it does. So why doesn't the Miller and Urey experiment prove that life originated in a primordial soup? What was it missing? Do we remember? So there were amino acids, but there were nowhere near enough of them. So it demonstrates that some molecules found at living things can arise under certain conditions, but that's all. It doesn't explain how we got here from there. So then we have Proterozoic life. So now our first traces of life that appeared 3.5 billion years ago in the early Archean, those were the little cyanobacteria guys, right? However, clearly identifiable fossils remain rare until late Archean. And that's when we get our stromatolites, those big old clumps of cyanobacteria. And those are layered. And those start to become a little more common in the rock record. So you can see here, we're seeing, oh, there's little, oh, we must have oxygen here because there must be some red stuff somewhere, right? So single-celled organisms. So now we have amino acids. All right, so this is where our little chain of steps gets a little fuzzy. But we know we have, volcanoes that put out the carbon dioxide that was necessary for the cyanobacteria to evolve and then breathe out oxygen. And the oxygen made it possible for more water to form too, but it also made it possible for respiration. So now we can do that, but these organisms can't form without the amino acids to form them. So yeah, we have cyanobacteria that can now breathe in carbon dioxide, but we still don't know quite how the cyanobacteria got there. Question? Yeah. Oh, this one? Okay, so single-celled organisms that belong to the kingdom Monera are prokaryotes. What's a prokaryote, Yusuf? No membrane-bound nucleus. So they have the components of a regular cellular nucleus, but there's no membrane around them. And then the more advanced is a eukaryote. Which are we? What are we? Are we prokaryotes or eukaryotes? What are we, James? Yeah, we're eukaryotes. Yeah, we're definitely, I'm a eukaryote, you're a eukaryote, we're all eukaryotes, right? All right. So they both have DNA as their genetic material. They both are membrane bound. They both have ribosomes. They both have basic metabolism. They both have amazingly diverse forms of life. Prokaryotes is a simple organism composed of a single cell. There's no multicellular prokaryotes. They don't exist, okay? And they have no membrane-bound nucleus, while your eukaryotes is an organism that can be single or multiple cells. And they have nuclei that are membrane-bound, and the cells in general are more complex. All right, so then what came next? All right, so next we have these fossils of soft-bodied Proterozoic organisms. These are, Precambrian fauna that came after that. And then what did we get, Yusuf? Yeah, biota means life. Fauna means basically more like animal life, not plant life. But biota would mean plants and animals, you're right. So then we had glaciation here. And then we had this widespread glaciation. That's how we ended our Proterozoic. And we leave these kinds of cells and these kinds of smaller organisms, and we get more complex. So in review, we're going to watch this one. And then I'm going to tell you one thing before you leave. Oh, no, we're not going to watch this one. This is the one I'm going to tell you to watch when you get home. You're going to be very excited because it's Professor Dave. Okay. This is going to be part of something you need to watch when you get home because it's 11 minutes. It's 11 minutes, and we don't have time for 11 minutes right now. But really, this is a good review. Okay. You really should make a point of watching it when you get home. If you have not done chemistry or biology with us, Professor Dave is the man. I knew you guys would be so excited. I even wrote, guess who's back? I even wrote it. Look, I said, guess who's back? You're going to be so excited because it's our friend, Professor Dave, right? Dave is amazing. Yeah, Dave is back. That's right. All right.
Pre or post haircut?
Now, this is pre. Okay, now wait, before you leave. All right. So watch Professor Dave at home. Professor Dave explains. Okay. Next week is winter break. Pay attention though. The week after is lesson 23. What's our lab? Mammoth lab. Okay, so it's going to be outdoors because I'm not bringing a baby pool of water in my house. I love you. Again, I don't trust you that much. Wait a minute. Don't leave yet. Wait, listen. Shh. Now, this is important and you need to understand this. The various books, various editions of your Earth Science book, some are produced like 1 year, like they're published 1 year off from the others. Some are published for specific states. The next few chapters might be wonky. You may have a chapter that's number something or other, but the content is something different on the syllabus. We need to really look at what the syllabus says. Like your next binder stuff, you will have things in there that say chapter 24, even though you're reading chapter 23. Follow along with what's in your binder. Look at what's there. And if you have a different chapter number in your book, stick with that. Okay? Just pay attention to it because it gets a little, because even here it says read chapter 23, but you're going to see chapter 24 in your notes. All right. So if you need to get money, come get money. And here are your answers for your homework. I'll put that up where you can see it.
If I have any, just give it to me.
Oh, yeah. Here, you don't want yours? Okay, here's, you want to hand them to her?
I don't really need.
I'll give, let me get hers too while I'm grabbing on those. I'm sure. What?
The ladybug.
Here, well, I know. Lily, here's the rest of hers. Okay. Two granny points. Oh, got them. Let's see, Piper, I'll help you out.
I think I just said Leah could have, but
Here, Piper. James, you want yours? Parker, can you reach him? Milo, you want yours? Chloe? Liam, you want yours? I was gonna say you wrapped up quite a few today. I would imagine you don't want to leave them. All right.
Oh, yay.
So Drew doesn't care. All righty. See ya in a week. Well, 2 weeks, Miss Sky.